Let's start with the topology, in which we are going to cover closed sets and limit points exercise. Start with the definition of a closed set. A subset A of a topological space H is said to be closed if the set H minus A is open. That is, the complement A is closed if its complement is open. That's what a closed set definition is. So we can easily verify that subset A comma B of R is closed because its complement, if you are taking the complement of A comma B, it will be like this, and here it is open, so union is also open. Similarly, closed A comma plus infinity is closed because its complement, you have to, if you want to say something closed, you have to take its complement and check whether it is open or not. So this is open, hence it is closed. Second example, in the plane R2, just in R2, the set x cross y, that is the Cartesian product of x cross y, such that x greater than or equal to 0 and y greater than or equal to 0. So it will be like a first quadrant with the axis. So because they have given greater than or equal to, so it will be first quadrant along with the axis. So in this plane, the set will gives you closed because its complement is the union of the sets, this one, minus infinity to 0 cross r and r cross minus infinity comma 0. Because if you just draw the graph, you can understand this. I mean, if you want to know what is complement, you can just draw a graph and you can verify this. Each of which is a product of open sets. This is open and this is open. Product of open sets of R and is therefore open in R2. This is product of open set is open. Next example. Going to the next example, I can just draw these two things because the complement you have to know where it takes. So here minus infinity to 0, that is here you should not take close 0 because the 0 is already taken in the set. We are taking only the complement, so 0 should not be included. Okay, so this is my x-axis and this is my y-axis coordinate. So r is my y-axis, so whole r will be covered. Hence this set will have this region, okay, whole region. These two coordinate fully will be coming, and here r is my x-axis. For y-axis I have to take only minus infinity to 0, that is here. So I will be taking this part. So when I take and, that is union of these two sets, I can have the complement of this set. This set in a sense my given set. So my complement is just given by these two sets. So the union of two open set is open. Why? How these two are open? Because the product of open is open. This is product of open sets. We know the result. Product of open set is open, hence it is open. It is also open. Union of two open set is again open. Therefore the complement becomes open. Therefore the set becomes closed. Here they have given one example with discrete topology. So discrete topology on the set X, every set is open, and it follows that every set is closed as well, because you know that discrete topology is nothing but the power set of X, the collection of all subset of X. So you have, in order to say discrete, if you want to list down a discrete topology, you can list down all the subset of X, that is nothing but power set of X. So that both are same. So you can verify easily that every set is both open and closed. You can see the last example here. Consider the following subset of the real line y equal to close 0, 1 union 2, 3. So this set you have to view in a way that it is a subspace topology. So in order to be a subspace topology, with respect to subspace topology, this 0, 1 is open, since it is the intersection of the open set minus 1 by 2, 3 by 2 of R. Minus 1 by 2, 3 by 2. It will be like from here to here. So I have taken this open interval and I have intersect with this my set y, so that I got 0, 1. When I get something out of it, then that becomes a element of tau y. Tau y is nothing but subspace topology on the set y. So I have got 0, 1, hence it becomes open. Similarly 2, 3 also it is open. I can say like 2, 3 itself with 2, I can take 2, 3 itself and I can intersect with this y, so that I can get this 2 comma 3. So it is even open as a subset of R. Since closed 0 comma 1 and 2 comma 3 are complements in Y of each other, so here with respect to Y, so when you are seeing Y, you cannot able to see the you should not say other element of the real axis, because you are restricting your uh, space to be Y. So in with respect to Y, you can see that closed 0 comma 1 is the complement to 2 comma 3. So these both are complement in Y. It is actually not the case when you see on the whole real axis, but with respect to Y, these both are complement to each other. We conclude that both 0 comma 1 and 2 comma 3 are closed subset of Y. Why? Because when you want to say it is closed, its complement should be open. You know, this is open, this is open. This is actually the complement of this. So complement is open means this is closed. So its complement is 0 comma 1. So when 0 comma 1 is open, this is closed. So we already got this is open, this is open. Now we are getting like this is closed, this is closed. So we can say that 0 comma 1 is both open and closed, 2 comma 3 is both open and closed. So this is the magic of this subspace topology. Let's prove this theorem. So for proving this, you have to consider the sets with the topological space. So with the help of topology only, we are going to prove all these three statements. So when you see the topology definition, you can see the similarities between those. Now firstly, phi and h are closed. In order to prove this, you already know it is a topology. I already told you, you should consider this as a topological space. So phi and h already will be there. So phi and h is already there, then that means phi and h are open. So if phi has the complement to be h and h's complement is phi. So complements are open, it implies the element are closed. So that's how phi and h are closed. Second point, arbitrary intersection of closed set are closed. But we know that in a topological space, arbitrary union of open set is open. But you have to just use the De Morgan law for just modifying that property of a topology. You know that x minus a alpha. A alpha is nothing but all the collection of closed set, because you are collecting the closed set and you are doing arbitrary intersection, and that thing should be closed. You have to prove that thing to be closed. That is nothing but its complement is open. So I have to take the complement of this. Arbitrary intersection of closed set is closed. You have to take the collection of closed set and do arbitrary intersection, but you cannot able to say it closed directly. So you have to say the complement to be open. So x minus intersection of there is arbitrary intersection of the element a alpha, all the element a alpha, which is equal to De Morgan's law is nothing but union of, you have to take this intersection to be outside, so it becomes union of x minus a alpha. So this is a very basic De Morgan law that is used here. So you are getting union of complement of a alphas. Since the set x minus a alpha are open by definition, how it is open? Because you know this is the closed set. So x minus a alpha, the complement of the closed set is open, you know this. So you have a collection of open set and you are taking arbitrary union of collection of open set. So that means it is open by definition. So before proving this theorem, you should know the definition of the topology. That's very important, because with that only we are proving all these three. So you know that arbitrary union of open set is open. Hence, I got arbitrary intersection of closed set is closed. So in the right hand side, I got it as a open. So what happens is that x minus, that is arbitrary intersection of closed set is closed, because its complement is open. So this becomes closed. Hence, intersection of a alpha is closed. Now finite union of closed set is closed. So for this, you should know the topological property, third property, that is finite intersection of closed set is closed. Finite intersection of open set is open. In the topology definition, everything will be revolve around the open. Okay, so with that only we are just extending to the closed one. Okay, So you have to say that finite union of closed set is closed. So yeah, you are taking some finite, so that means the index should be from 1 to n. You should not go to infinity or something. So it should be finite. So I'm taking ai which is closed and some finite collections. I have to take finite union. So finite union I have to take, and I have to take that to be closed. I have to say union of ai is closed. In order to say that union of ai is closed, I have to say complement is open. So x minus union of ai I'm taking, and this one by De Morgan's law it comes outside, that is intersection of x minus ai, and we know that finite intersection of this is open because ai is closed. So ai is closed, x minus ai is open, finite intersection of open set is open. Hence I got right hand side to be open. So this becomes open, that is complement of ai becomes open. Hence I can say that the union, finite union of ai, finite union of closed set is closed because the complement is open. So hence I have proved all these statements.